talk about tandem mass spectrometry. If you want to get a little bit of the best of both worlds, that's why you do tandem mass spectrometry. Plus, as I mentioned earlier, you can do some fragmentation and get even more information. So that's where you can start getting into structural details. So again, to remind you, the mass spec has an ion source, there's a mass analyzer and a detector. And if you just have one mass analyzer, you're measuring the mass discharge of the ions that go through that mass spec. If your source is a gentle source like ESI, you're going to be measuring the mass of the intact parent molecule. If the source is a higher energy and like a electron impact, you're going to be breaking your molecules apart and you'll be measuring the mass discharge of fragments. When tandem mass spectrometry, you generally want your ion source to be gentle so that in your first mass analyzer, you can measure your parent or intact molecule. And then there's something here, it's called the activation cell, could be called the collision cell. Normally that's what people call it now. And you have an inert collision gas that goes in there with high energy that breaks your molecules apart. And then you measure the fragments in a second mass analyzer. And so here you will get the same sort of readout, but you'll get one of these for both mass analyzers. And the information you get at the end is kind of like a puzzle that you can piece back together to figure out what the original intact, because you have the sort of parent mass of the molecule and you have the fragments, and you can figure out how it all fit together usually if you're doing really good mass spectrometry. So short form for tandem mass spectrometry is MS/MS. And so this is my own little, I don't know, I made this many, many years ago. It's like an animated version of this. So just to sort of reinforce. The ions get ionized in the source and they travel to the first mass analyzer where we scan, measure, and select and filter for precursor ions, depending on what your goal is. So here you can measure the intact molecule of the precursor ion. And then you've got the collision cell, where an inert gas will come and break those things into what are called product ions, because it's a reaction. So you've got your precursor ions as your parts of the why can't I not think of the words? The thing starting the reaction, undergoing the reaction, then you have a product after your reaction, so the product ions. And then in your second mass analyzer, you can measure those product ions and understand them. So what you send to the detector are the masses of those precursors and products. Now, if you're doing tandem mass spectrometry that's connected to a sample introduction system like an LC or a GC, you get some extra information. So let's say you have a complex mixture. You put that complex mixture onto your column. You should get some separation based on polarity or what other kind of properties you're using to separate your mixture, depending on your column and your solvents. And then each one of those peaks hits the detector, which is, in this case, I'm going to write in Q-top. It could be whatever your tandem mass spectrometer is. And what you get there is a signal that is in a chromatogram. So you've got time on your x-axis and the intensity or the size of those area of those peaks as your y, as your signal intensity. And so the smaller the number of ions, the smaller the peak, and the bigger the number, the bigger the peak. And then if you compare or combine that with the same information that I just showed you for tandem mass spectrometry, you then, for each one of these peaks, you get precursor ions mass measured. Sorry, I hit the wrong button. And then you also get the product ions from those precursor ions measured. So when you run samples on our LC Q-top doing MSMS, you get 3 dimensions of information. If you're doing metabolomics or proteomics, the cool thing is that in the first mass analyzer, and even maybe oligos, the first mass analyzer is going to measure the intact oligo or peptide or molecule. And then from the second mass analyzer, if we're talking about something with a sequence, like a peptide or an oligo, you could technically get the sequence information. And then if we're talking about a metabolite, you can figure out maybe what specific metabolite you have. Can you resolve one amino acid from another that maybe has a similar similar behavior in the HPLC column, but then has a different mass and different fragments. So with these 3 dimensions, you can actually plot your data in 3 dimensions. So you can have retention time, your parent mass charge ratio, and intensity, and you can make 2 of these for each mass analyzer. All right. So as an example of tandem mass spectrometry, I'm going to show you how our mass spec here at Ontario Tech, the QTOF, works. So this is a quadrupole time of flight mass spectrometer. This measures mass based upon time that it takes for the ions to make it through the flight tube. And so calibration is really important. These instruments don't tend to lose their calibration very often unless you purposely mess them up. But it is important to calibrate. They have relatively high resolution, just going back over the information I've already told you. You can distinguish isotope patterns with a QTOF with this level of resolution. So you could do the same with an Orbitrap or magnetic sector, or yes, and those ones are the really good ones, or an FTICR as well. You can get isotope patterns. And you are able to distinguish molecules with confidence to 3 decimal places. So this is a little animation, but I'm not sure it's going to work because lately my animations aren't working. Yeah. So there's an animation here that I have to figure out how to play that shows you that quadruple time of flight. Let me see if I can figure that out. Give me a second. I'm going to stop presenting and see if I can make it happen another way. I got this new computer and it came with a new version of PowerPoint, and it won't play any of my videos now. It's been really frustrating during lectures this year as well. So I think this one, what I'm going to do is I'll just go to YouTube. I know it's on YouTube or Agilent's website, so I'll just find it. And then I'll put it on the screen that I'm recording and share my see it. So give me a second. Share the screen. Then I'll go back to the presentation and get the link to the next one and do something similar. So yeah, here's the one. All right. So make this large. Hopefully the sound will come through too.
Whether you are identifying proteins and characterizing post-translational modifications, searching for metabolite biomarkers, or finding impurities in pharmaceuticals or food, the Agilent 6510 Quadrupole Time-of-Flight LC-MS is an outstanding choice. It delivers better than 2 ppm mass accuracy for MS and better than 5 ppm mass accuracy for MSMS. It also delivers wide in-spectrum dynamic range and unsurpassed QTOF sensitivity, all in a reliable and easy-to-use system. Great sensitivity starts with superior ionization technology. Agilent's patented nebulization technology produces finer droplets and delivers more ions to the mass spectrometer. A second nebulizer introduces reference mass solution that ensures continual mass axis correction for the best possible mass accuracy. High-volume counterflow drying gas reduces noise related to incomplete drying of solvent droplets and keeps the sampling capillary and ion optics cleaner for reduced maintenance. A thin skimmer aperture, carefully matched hole size, and short capillary to skimmer distance reduce beam broadening. An on-axis octopole ion guide provides nearly 100% ion transmission over a wider mass range. Patented lenses enhance high-mass ion transmission and increase sensitivity over a wider mass range. The quadrupole mass filter allows only ions of the target mass to pass through. The hyperbolic shape of the rods enhances ion transmission and spectral resolution. In the hexapole collision cell, precursor ions strike collision gas molecules, generating product ions and neutral fragments. Linear axial acceleration and high collision gas pressure ensure that all ions exit the collision cell with nearly identical energy. This allows the same mass calibration factors to be applied to MS and MSMs ions. The result is better than 5 ppm mass accuracy for MSMs ions. Another octupole ion guide keeps the ions together while allowing excess collision gas to be pumped away. A quadrupole ion guide flattens the stream of ions for better transmission through the slicer. The slicer reduces variations in the vertical momentum of the ions. Ions with too much vertical momentum do not reach the pulsar. This improves mass accuracy for all ions. The flight tube is constructed of special materials with very low coefficients of thermal expansion, so it is less sensitive to temperature changes. The reflecton compensates for minor velocity differences, improving the resolving power of the 6510. The microchannel plate detector converts the ion signal from electrons to photons and back to electrons. This electrically isolates the high voltage flight tube and front of the detector from the signal passed to the electronics. ADC digitizer electronics provide extremely high mass accuracy over a broader dynamic range. The 6510 offers outstanding in-spectrum dynamic range for a time-of-flight instrument. When you need the ultimate in LC, MS, MS power and versatility, the Agilent 6510 QTOF provides it, with an ease of use and reliability rarely found in a research-grade mass spectrometer.
I'm going to pause it now because it's back to an ad, but the animation's really cool. So now I'm going to show a similar video to the TIMS TOF that I want. Now, I happen to favor Agilent, and I'll tell everybody why after this video, but I'll do a quick, it's not on a slide because I don't want to write it down, but I'll give you guys sort of my quick take on the different companies and why I prefer Agilent. I haven't worked with every instrument to say, but by reputation, I know a little bit about the different mass specs. So here is another video, but it's on Agilent's website. I'm just going to make sure that the volume and stuff is up. It's another ad, of course, but this is for the cool TIMS TOF, which is a ion mobility time of flight tandem mass spec. I don't know. I think that's as big as I can make it. So hopefully this will. So weird that I can't just open it in another tab. No, that looks a little better. Okay.
Whether you are searching for metabolites or protein biomarkers, characterizing proteins, increasing metabolite coverage maps, or ensuring food safety, the Agilent 6560 Ion Mobility QTOF LC-MS is an outstanding choice for resolving complex samples. Ion mobility technology greatly enhances molecular specificity. Based on differences in molecular shape and charge, this technology adds a new dimension of separation, which can be immensely beneficial when analyzing compounds in complex samples. The Agilent 6560 Ion Mobility QTOF LC-MS uses high resolving power drift tube ion mobility that facilitates direct determination of accurate cross-sectional area measurements without the need for calibration standards. It also delivers high data quality with better detection levels and dynamic range than conventional ion mobility mass spectrometers. The Agilent 6560 Ion Mobility QTOF LC-MS incorporates innovations in jet stream ionization, I-funnel enrichment, ion trapping, uniform field drift tube, and rear ion funnel. High sensitivity detection starts with the Agilent jet stream ionization technology. It produces a significantly larger number of ions from the liquid spray in the source region that results in increased ion sampling. A second sprayer introduces a reference mass that ensures the best possible mass accuracy and calibration. The first section of the ion funnel operates at high pressure, where funnel DC and RF voltages propel ions toward the trapping funnel. This ion funnel enriches the ion population and allows excess gas to be pumped away. Then, a trapping funnel operates by first storing and then releasing small packets of ions into the drift tube. The continuous ion beam from the electrospray process is now converted into a pulsed ion beam. Each packet of ions is then resolved in the drift tube based on the mobilities of ions, which are determined by their size and charge. Ions with higher charge states experience a higher electric force, resulting in a higher drift velocity. In addition, ions with larger collisional cross-sections undergo higher numbers of interactions with the drift gas molecules and migrate through the drift tube more slowly than smaller ions. The combination of both factors determines the overall velocity of the molecule and hence results in arrival time separation at the end of the drift tube. The design of the Agilent ion mobility drift tube is a significant advance over other commercially available IMS instruments. It enables the direct determination of molecular cross-sectional areas, a key capability for research applications. This arises from the use of a drift region operated under uniform low field conditions, unlike other IMS instruments. Ions exiting the drift tube are refocused by a rear ion funnel to ensure high-efficiency transfer into the ion guides before they enter the collision cell. In the collision cell, precursor ions undergo collisions with gas molecules, generating product ions. All the product ions are further accelerated through a middle focusing lens to reach the pulsar. All the ions are then pulsed upwards into the time-of-flight analyzer with an extended mirror reflectron, which increases resolution and compensates for velocity differences. The flight tube is constructed of a special material with extremely low coefficients of thermal expansion, so it is much less sensitive to temperature changes normally seen in day-to-day lab operation. The microchannel plate detector converts the ion signal from electrons to photons and back to electrons. 4 GHz digitizer electronics provide excellent mass accuracy over a broad dynamic range. Advanced Agilent Mass Hunter software provides comprehensive view of 4-dimensional data with flexible navigation and data mining. Fast and accurate calculation of collision cross-sections can be easily achieved. Customized views of graphics makes browsing simple and fast. When you need to analyze complex samples, the Agilent 6560 Ion Mobility QTOF LCMS provides the additional dimension of separation to minimize interference and enhance signal-to-noise, raising your measurements to a new level of...
Okay, definitely still an ad, so I'll just close that now. Okay, so detectors. So there are a few different styles of detectors. The Faraday cup was one of the original ones, and this is usually used on magnetic sector and electronic sector instruments. This is literally a cup, and the ion beam travels into it, and the electrons then sort of hit the walls of the cup, which sends a signal, like a current signal, to an amplifier. It's actually pretty simple and elegant and works really well. Electron multipliers take ions in and multiply the signal as they bounce off these different sort of, I don't know what they're multiplying plates. These are most common in quadruples, and the signal out can get intensified, and that's why they're quadruples, for instance, who use these often, quadruple mass specs, triple quads tend to be really sensitive because you can take the signal from one ion and really amplify it. The photomultiplier, which is the one that you would have seen in that video, it does multiply the signal, but not quite as heavily as an electron multiplier. But it's sensitive because the detector that's measuring the photons, or maybe not sensitive, but it's maybe, I'm not sure what the best word is here. It can last longer because it's measuring photons, and so therefore it's sensitive, but it also has the ability to not sort of like run out of charge, whereas an electron multiplier can. And this is basically just the way these different detectors work. So not all detectors are created equal. When you're doing non-targeted acquisition, which I'm about to teach you guys about, different data acquisition modes, I prefer detectors that can handle a long lifetime of detection. So when you're doing non-targeted, especially all ions or what people call swath or data independent analysis, you can literally burn out your detector, and that's why they tend to go so quickly on those other instruments. So when you're going to purchase a mass spec, if you're ever on the market for one, be sure to ask about detector life, and all the companies will tell you their detector life is great. So in fact, find people who are using it and ask them how often they've had to change their detector. That's the only way you're going to know. Okay. Data acquisition. So non-targeted data acquisition improves both. Okay, sorry, I'll back up. Improvements in both resolution and speed of mass spectrometers has allowed us to do what's called non-targeted data acquisition. In the old days, you had to specifically look for one mass. You had to know what you were looking for. You had to set your mass spec specifically to that. You had to do all the math, and it was a pain in the ass, and it took a long time. But now, because everything can go fast and our processors, our computer processors are quick and they're amazing at doing math for us, we can let the instrument sort of do all the work for us. And we can measure all the ions coming in the mass spec instead of just saying, look for this one. So this means we can look at things we don't know anything about. So we can identify our compounds after the mass spec has collected all its data, and based on the data that's acquired, we can figure out what was in our sample. Non-targeted tandem mass spectrometry has catapulted proteomics and metabolomics into mainstream use. So this is sort of what non-targeted data acquisition looks like. So you have your ions coming in from the ion source. When it's, this is what targeted approaches look like. I'm just reading the slide and I should have looked more closely. These are targeted. So you're targeting because either in your first mass analyzer or in your second mass analyzer, you fix on a specific target or a specific mass. So you filter for one mass and then you might scan all the fragments, or you might scan all the masses and fix in on one fragment, or perhaps you'll fix in on a mass, do collisional induced dissociation, and then fix in on a fragment, one single fragment. This is called single reaction monitoring. This is called multiple reaction monitoring. And I'm not sure that this has a term. Parallel reaction monitoring, perhaps? Okay. In the non-targeted approach, you scan everything that goes into your first mass analyzer. You do collisional induced dissociation, and then you scan everything that comes out. Now, there's two ways to do this non-targeted approach, which I'll talk about in a minute. Try not to rush too quickly. So the data-dependent method is where each precursor is sent to the collision cell based on a decision engine. So you'll have some criteria, maybe the top 10 most abundant, the charge state, the isotope pattern, something that looks like a chlorine, anything that looks like it contains a chlorine, send it to the collision cell. And the filter, the first mass analyzer will send one at a time to the collision cell and then scan all of the product ions. So the first scan is called a survey scan, and the masses from the survey scan that are selected based on your decision engine criteria get sent one at a time. So you get MS2 or fragmentation spectra for each one of these things that are selected in the survey scan. This is another way to look at it. And there's different ways that you can select. So here they're showing you, it says threshold, but it should say threshold. Sorry. So this would be the threshold or abundance model. So like I said, it's only one at a time. This can capture a portion of the precursors present in the first mass analyzer at any given moment, but only a portion. Sequence coverage will then be limited to the precursors that get selected by the decision engines. So this means that low abundance peptides might not get it selected, or low abundance oligos, or whatever else you have in your mixture. But you get very clean product ion spectra. And the cleaner the product ion spectra, the more confident you can be in the identifications you make after the fact. Data-dependent acquisition, this is another sort of image. You guys can look over this slide later since we're running kind of short on time. This is what we do right now with our QTOF here, if you're doing proteomics or metabolomics in my group. And it's called auto MSMS. That's the type of DDA we're doing. And then we use Spectramill and Skyline to sort out the data after the fact. Then with data-independent acquisition, all precursors are scanned in the first mass analyzer, and there's no filtration. Every precursor, I mean, you can still put some criterion, like maybe of a certain range of masses, for instance, and then you send all the ions to the collision cell. Then the collision cell creates product ions, and all the product ions then get measured in the second mass analyzer. So it sort of looks the same here, but usually they do it in what's called selected widths, or SWAF, which is the SciEx coined this term called SWAF. So you have selected widths that you send, everything in this mass range, and then you do all of your fragments, and then you do everything in this mass range, you do all your fragments, so on and so forth, until you've collected all of product ion spectra for the entire mass range of your survey scan. So this tends to look like little mass windows and in steps, and you're isolating a larger width of masses, not just a single mass. But this product ion spectra is a mixture of more than one precursor ion. So it's super complex, it's much more difficult to interpret, and actually in the end of the day, while you get full coverage and you could probably capture more low abundance ions this way, funny enough, the only way to analyze this data is to do a couple of DDA runs to build a library, and then you go back and interrogate the data with your DDA data-dependent acquired information in order to figure out what's there. So here's another similar picture to the other one I showed you that just sort of summarizes it if you want to go over it in more detail later. We can do this with the 6545 that we have in what's called all ions mode, and then also with Spectramill and Skyline, but we haven't tried it yet. Actually, I don't think Simon's here, but one of the goals I have with Simon to try in the next month is our all ions and see how it works. All right, so the last thing this is my very last slide, I think, so don't worry, we're almost done. I know we're running a couple minutes late. I hope you guys can stay. And Ev and I think it's John or maybe Elmira, we have a meeting after this. I hope you guys don't mind if we start 2 minutes late. Okay, so iterative DDA, here is when you perform data-dependent analysis with your decision engine, but with a twist. The first time you run it, the mass spec will save the information from that first run. And then you do it a second time, and when you do, you tell it not to look for any of the ions that were in the first set of survey scans. So your second run will have survey scans with fully new sets of ions. And so the idea is that in your first run, you may capture all these high abundance ones, and then your second one, you'll catch some middle abundance ones. And if you do this enough, you'll get all the way down to the bottom of the noise. You can do as many iterations as your sample of that volume will allow, because of course this is injecting the same sample over and over, so you need to be less sample limited in this model. But this is how you can build up a much more comprehensive picture of what's in your sample. So we've been trying this a lot more in our lab lately. Linda's been doing iterative DDA with the wastewater samples, and Simon and I are also trying this. But as well, when you want to do DDA, it's really nice for metabolomics, for instance. This is for you, Ev. When you take a composite sample, say of all of your samples, you make a composite. So you have lots of sample now. You take a microliter from each of 50. Now you have 50 microliters. And you do an iterative run using DDA mode on multiple injections. This should give you an idea of everything that's in all of your individual samples. And then you can use that data to go back and interrogate each individual sample. So if you wanted to do an iterative DDA to build a library, which you then used to interrogate a data-independent analysis, this is the gold standard right now. However, when you're doing data independent, remember it does shorten the life of your detector. So if you can just get away with iterative DDA and say run each sample twice and still get lots of information, then you can. And the drawback, it requires more sample and more time. So Sarah's running. Thank you, Sarah. We'll talk to you soon. I'm actually done. So are there any questions?